All right, welcome back, folks. In the last chapter, we talked about hypothesis tests and how to do hypothesis tests with a single sample, whether we were using proportions or we were using means to determine those tests and whether we knew the population standard deviation or not. Right? So we learned how to do a one sample Z test. You learned how to do a one sample T test, and you learned how to do essentially a one sample Z test with proportions. In this chapter, we're going to talk about how to answer questions about two samples. In this section, we're going to talk about how to answer questions about two independent samples. In the next section, two different samples of proportions. And then in the last section, we'll talk about paired samples. And so in this section, we're going to talk about the difference between independent and paired samples. And then we're going to perform some hypothesis tests using independent samples. And then I'm going to show you how to do the same types of hypothesis tests with a confidence interval. When we talk about independent samples in a research study, we are comparing two samples where no one in the first sample is in the second sample. And so the observations in one sample do not influence the observations in the other sample. Right? So if you're asking people questions, then the participants aren't in the same groups. If you're measuring something else, then you're not measuring those same groups twice. Right? Everything in one sample is not in the other sample. Okay, that makes them independent of one another. Paired samples are when you measure something twice or you have pairs that are matched. Okay, so each observation in the first sample can be paired with one in the second. So you measure something before a treatment and then you measure something after a treatment. This would be a paired sample. You're measuring the same people, the same sample twice, just before and after. And so it would be a matched pair. Okay, you can also do this by matching students in a class based on their ability, right? So if you wanted to break up a class based on math ability, you could take the highest performing student and the second highest performing student. And they start the two groups. And then the third highest performing student goes with the second, the fourth highest performing student goes with the first, and so on. And then you would have groups that are essentially matched on math ability. Those two groups wouldn't be the same people, but you could then think of them as a paired sample, right? Or as a matched pair. Okay, so it doesn't have to be always measuring the same thing before and after, but with paired samples, you want the measurements to be related to one another in some kind of way. All relates back to the way that these values vary. Independent samples can vary independent of one another, whereas a paired sample are going to vary similarly. And you'll see that it changes how we calculate some things as we go forward. So let's talk about a two independent samples t-test. First of all, when we're dealing with a hypothesis test for a difference in two independent samples, we're going to assume that we have two random samples from two populations and they're independent of one another. And then we want to have a sample size that's either large or we want a population that's approximately normal. And so this is just means a symmetric population so that we can use all of the things we've been learning about. Okay, so this again means that we're talking about values where the mean is the best measure of center, and so on. In order to write the hypotheses for these tests, right, remember the null hypothesis is the statement of equality. So it's the idea that the two samples are equal to one another. There's no difference. One's not greater or less than the other. Right? And so the null is always the statement of equality. And then we have a left-tailed, right-tailed test or a two-tailed test, depending on whether we think one group is less than, one group is greater than, or whether they are different from one another. And again, that comes from our research question and what we're trying to answer. The biggest difference between a one-sample t-test and a two-sample t-test is that in a two-sample t-test, the calculation for t is a little bit different. Okay? And again, it goes to the idea that we just have to change the way that we measure the variance or the standard error of the possible samples that we could find. Okay, and so this is really the only part that's different. And we just have to account for both of our samples. This is the standard deviation from the first sample size from the first sample. Standard deviation from the second, sample size from the second. Okay, and to find our degrees of freedom, it is just the sum of the two independent samples minus 2, or n minus 1 for both samples. And that will give you your degrees of freedom. For two independent samples, it's easier just to think about it as the total minus 2. So let's take a look at some examples. A researcher wants to determine if there's a difference between the average GPA of students who enroll in music courses and those who do not. And so we've got students in music courses and students who are not in music courses. Sample of 45 students is randomly chosen from each group. We're given the mean of each group, whether they're in a music course or not, their standard deviations, and then the sample size. We're going to use a significance level of 0.05 and determine if there's a difference in the GPAs. And so here we want to determine if there's a difference, not whether one is greater or less than. And so first we're going to state our hypotheses. And you'll see that as we go through this, the steps that we use for the hypothesis test are the same. We're just going to change up what happens at each step. The null is that the mean of those who are in music classes, remember mean 1 is music, mean 2, no music classes. The null hypothesis is that they are equal. We're going to assume that the two start out being equal. The alternative is that they are different from one another. They are not equal. That the mean and GPA of students in music classes is not equal to the mean GPA of students that are not in music classes, or it's different from. We would then want to calculate the test statistic. Okay, we're going to need the degrees of freedom as well. We have two samples of 45, add them up and subtract 2, and we get a degrees of freedom that's equal to 88. We're just going to hold on to that because we're going to need that in just a minute. To calculate our t-value, if you go back and look, here's our means, standard deviations, and the sample size. And so we're going to plug those in here. And if we calculate these values, we get a t-value of negative 0.93. Now that we have our t-value, everything else, like the previous hypothesis test, is very similar. Okay, we want to determine if there's a difference between the average GPA of those two students with a significance level of 0.05. And so if we wanted to find the critical t-value, that would mark our rejection region, right? And so that's at about 2. And since it's a two-tailed test, it would be on both sides. And so this would give us 2.5% here, 2.5% here. Okay, but if we look for where our t-value actually is, the other t-value we found, negative 0.930. So that would be here. That's the t that we found from our sample. We'll for a slightly better color. That'll work. And you can also see that the t we found is at least an absolute value less than the critical t-value. Okay, we can also calculate the probability. Okay, we found the p-value, or the probability is 0.35 or 35.49%. And that would be the probability essentially on either side of t here. So much greater than 0.05 or our significance level. And so in both cases here, we would fail to reject the null. There's no evidence to support that the mean GPA of students who take a music class is different from students that do not take a music class. We found the probability is 35.49%. Right? So what this means is that there's a 35.49% chance that if we randomly chose two samples again, we'd find this exact same difference, right? Which means that it's not a rare sample. It's not unlikely to happen by chance. It could easily happen by chance. Now I went through that example and showed you all of the steps already worked out. In the next example, we're going to do this one together. Are low-fat diets and low-carb diets more effective for weight loss? We have a sample of 77 subjects who went on a low-carb diet for 6 months, and they lost 4.7 kilograms. So their mean loss was 4.7 kilograms, their sample of 77, and the sample standard deviation of that group was 7.16 kilograms. We have a second mean loss of, well, the second group went on a low-fat diet. Okay, so this is, let's just use C and F here. And so for the low-fat diet, the sample mean weight loss was 2.6 kilograms with a standard deviation of 5.9 kilograms. Can we conclude that the mean weight loss differs between the two diets? And we're going to use the critical value method for an alpha level of 0.01. And here our second sample size was 79. Okay, so first we want to state our hypotheses. Remember that the null hypothesis is that the two groups, the mean weight loss of the carb diet is equal to the mean weight loss of the low-fat diet. The alternative, we're trying to conclude if they're different. And if they're different, then we would use not equal to. And so in this case, we're going to have a two-tailed test. We now want to calculate the test statistic. So remember, it is our sample means, and it does not matter the order if we're doing a two-tailed test. The square root of S1 squared over N1 plus S2 squared over N2. Okay, and so the mean of the low-carb diet, 4.7 kilograms. The mean of the low-fat diet, 2.6 kilograms. The square root of the standard deviation of the first group, 7.16 squared divided by 77, plus 5.9 squared divided by 79. In the numerator, 2.1. When you calculate the value in the denominator, be careful. Make sure that you square the values before you divide. You should then get the square root of 1.106420, or 2.1 divided by 1.05186, or 1.996. So our t-value that we calculated, 1.996. And here, our degrees of freedom, 77 plus 79 minus 2 use 154. And so now we need the degrees of freedom, and we have our t-value was 1.996. We want to use the critical value method, so we need the critical value for t, and I'm going to switch the colors up just a little bit from the last example, but we want to find the critical value of t. Okay, to do that, we can use Excel. Equals here, it's a two-tailed test, so equals equals t.inv.2t. Okay, we have a 0.01 level of significance, and our degrees of freedom is 154. When you plug that into Excel, you get a critical t-value of 2.608. So 2.6 for the critical t, somewhere over here. Remember, for a two-tailed test, it's always plus or minus this. And the reason that is we could have gone back, remember, and switched these two around, and then this would just be a negative value. And so it's always plus or minus in that case. When it's a two-tailed test, you're not looking for one to be greater than the other. But notice that our t-value is not within the rejection region. And we could also find the probability, the p-value in Excel, t.dist.2t, and then 1.996, 154. And we find the p-value is 0.0477 or 4.77%. But remember, we're looking for a significance level of 0.01 in this case, so it's not less than 1%. Okay, and so in both cases here, right, whether we use the critical value method or whether we find the p-value, we are going to fail to reject the null. There's no evidence to conclude the mean weight loss differs between two diets. Finally, I mentioned in one of the previous videos that you can use confidence intervals to answer these same questions. So let's take a look at how to do that here. If we want to find the confidence interval for the difference of two independent means, we have our mean difference plus or minus what is our margin of error. It's just calculated slightly differently, but it's very similar to the t-values we just calculated. If the confidence interval contains 0, then you're not going to have a difference in the means. In other words, no significant difference, because that means that the mean difference could be 0. If 0 is outside of the interval, then there would be a significant difference. Sample of 87 one-year-old spotted flounder had a mean length of 126.31 millimeters, sample standard deviation of 18.10. A sample of 132 two-year-old flounder, mean length of this, and a sample standard deviation of this. We're going to find that 95% confidence interval. Well, the first thing we need in order to do this very easily is to find our critical t-value. And again, this will come from a table or come from Excel. We need our degrees of freedom. We have 87 and 132. 87 plus 132 minus 2. The degrees of freedom are 217. And so to find our critical t-value, we want to use equals t. Here we're just looking for the difference. When we're finding a confidence interval, it's always a two-tailed process. Equals t.inv.2t. Okay, if we want a 95% confidence interval, then we want 5% outside with degrees of freedom of 217. And that will give us a critical t-value of, once we plug it into Excel, 1.971. And so now, if we want to construct this confidence interval, we want a 95% confidence interval. And then we need our mean difference, the mean of the first group, 126.31. The mean of the second group, 162.41. Well, since we're just comparing the two, let's flip those around just to make that difference positive. In general, it would not matter. It's just a little easier to talk about. And so this is x2, or n2, I'm sorry, and this one would be n1. Plus or minus our critical t-value, 1.971. And then we got to find our standard error term here. This is S1, the standard deviation of the first sample. I'm sorry, of the second sample is 28.49 squared divided by 132 plus 18.10 squared divided by 87. And so if we calculate, I'm just going to move down here just a little bit. Let's first subtract these two. 126.41 minus, I'm sorry, 162.41 minus 126.31 is going to give you 36.1 plus or minus 1.971 times. Now we've got to find this thing here. Remember, just to be careful, in your calculator, you want to square 28.49 squared divided by 132 and so on. And if you work all this out, you should get 3.1488. And so that'll give us a confidence interval 36.1 plus or minus 6.21. And this is actually 10 if we want to write it that way. And so that gives us a range of values for our difference between the 2-year-old flounder and the 1-year-old flounder of 36.10 minus 6.21 is 29.89. And then 36.10 plus 6.21, 42.31. And so we can be 95% confident that the difference in the mean length between 2-year-old flounder and 1-year-old flounder is between 29.89 millimeters and 42.31 millimeters. Now we use the confidence interval to answer the question about the mean length, but notice that this confidence interval does not contain 0. If you were to then go and calculate the t-value as we did before, okay, you're going to find that it's greater than this critical value because 0 is not included in the interval. In the confidence interval, we can be 95% confident that the mean difference between them is not 0. And so that means that they're different, less than 5% of the time. We'll do more examples like this in the next few sections with proportions and with paired samples. Please let me know if you have any questions.